So I will start today's class. So I will record this and I will share in the LMS as well. We had some discussions in the last classes regarding different laws like Coulomb's law, Gaussian law, Faraday's law, Ampere's law, and so on. So in the last class, we have discussed those laws and we have discussed how we can mathematically model those laws. So actually, the reason that we were learning those was for us to understand how we can apply it for electromagnetism and how we can formulate the Maxwell's law, which is used to describe the electromagnetic waves and how electromagnetic waves gets generated. So the kind of the magic about the Maxwell's law is that Maxwell found that we can generate electromagnetic waves that can propagate through the vacuum even without any kind of source, like source charges, without any charges, depending on the electric field strengths and magnetic field strengths, the wave can propagate forward. Just depending on the magnetic and electric fields, the wave can be propagated forward through the space, through the vacuum. That was the important discovery that Maxwell had in contrast to Ampere or Faraday or Gaussian or Coulomb. So they were basically moving or discovering facts regarding electric charges and what happens in the presence of electric charges, while Maxwell thought we do need the electric charges or some kind of a source initially, but after that the 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 electric field and magnetic fields are generated, uh, the 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 change in the electric field and magnetic fields can generate another set of electric and magnetic fields, and that the second generation of electric fields and magnetic fields can generate another third generation of electric and magnetic fields, which are actually changing with the time, and because of that nature, the electromagnetic wave is generated, and just having those propagation or the electric fields and magnetic fields, the wave will propagate. So we will learn about that fact in today's class, right? So mathematically, we are going to learn those facts and write the equations that show that the electric field or the electromagnetic wave can generate without any electric charges. So we will use the knowledge we have regarding Faraday's law, Ampere's law, and Gaussian law to derive the Maxwell's law, which says about that. Okay. So in the last classes, we have talked about the basically the other laws. So I will write them one by one, and then I will discuss about the Maxwell's law, which combines all those laws into one set of equations, uh, which can mathematically model an electromagnetic wave. So, uh, so the discovery of electromagnetic waves took years, and it was a very historical thing. So I think you have already seen like multiple times that I have mentioned about these historical like scientists and the laws that they presented. So Coulomb's law, Gauss's law, we discussed. So in Coulomb's law, we discussed about the force between charges, between mainly two charges. If we take, for example, in a free space with distance between them, and how the force will get created. And using Coulomb's law, we can determine the electric field at a certain point in the space. So next, Gaussian law. It was considered in two ways. So Gaussian law was described for the electric field and also for the magnetic field. So Gaussian law was can also be divided again into two parts. Like under electric field, we have the integral form and the differential form. So we have equations for those different scenarios. So integral form means like we are taking the integration over a certain closed surface of the electric field across the that is generated out of the closed surface is equal to the total enclosed charge over the epsilon naught, which is determined by the medium through which the wave is propagating. So then the differential form says that the total electric flux that is going out from a certain closed surface at a certain unit point is equal to the unit charge at that, unit charge per unit volume over epsilon naught. So these were the equations actually that we have already discussed. So anyway, so you know these things. So when we take the magnetic field based Gaussian law, we have the similar equations. So for the integral form, we have the magnetic field over a closed surface is equal to 0, and the total divergence of the magnetic field is also 0. Then we have Faraday's law. Faraday's law, that also we have in integral form and differential form. So in last class we discussed this. The total the electromotive force that is generated around a certain loop is equal to the rate of change of magnetic flux through that loop. Okay, so if you have any questions, you can ask, right? So we can write in both integral form and differential form. So right. So the curl of electric field is equal to the rate of change of magnetic flux per unit time through the loop. So the curl of electric field at a certain point is equal to the amount of flux changing at that point per unit time. The minus sign is coming because of the Lenz law. So therefore, in Faraday's law, we have both Lenz law and Faraday's law combined. The effect of Lenz law is given by the negative sign. So then we discussed the Ampere's law. The Ampere's law says it tells about the magnetomotive force, which is getting created due to a certain current, which is varying over a certain surface or a loop, right? So we can write that also in integral form and differential form. So similar to like Faraday's law, we can write that the total magnetomotive force generated as an integration. So we write L in here to show that the magnetomotive force is generated at the edge of the surface, and it is caused by the charge the charge density that is available in the surface, and the rate of change of electric field across that surface. Wait. When we take the amount of magnetomotive force per unit area, then we consider the curl of B, and it is equal to the mu naught J, which is the charge charge density per unit area. So charge density per unit area plus the mu naught epsilon naught dabba E over dabba T. So which denotes the rate of change of electric field across that surface that we are considering. So in here, in this integration, we are taking the total amount of electric field that is changing over the total surface. So that is why we are taking the integration over area of A, which represents the surface area uh, of the metal loop, or the metal sheet that is covering the metal loop. So in here, in the second equation, we are considering about a unit area. So because of that, we do not consider the entire area in the second equation. In there, we consider unit area, and we consider the electric field change over that unit area per unit time per time to calculate the amount of magnetomotive force generated around the boundary of that surface through which the magnetic field is, through which the electric field is varied. So those were the equations that we were going through in the last class. However, like in these all these equations, as you see, all these equations are relying on the free charges, electric charges that are causing these electric field or magnetic field to generate. Right. In all these equations, we require some electric charges to generate the magnetic field or electric field. Maxwell was the next scientist which tried to solve this, solve or bring these equations in such a way that that he was able to one thing say that an electromagnetic wave can propagate without free charges after it has generated, and other thing is that he was able to show that uh, the fact that a change in I will say that later as well. A change in electric field results in when we are varying a certain electric field, we can generate magnetic field. We can generate magnetic field, right? So once we are changing the electric field, once we are changing the magnitude of electric field, right, we can generate a magnetic field, right? And if that magnetic field also is changing with the time, right? If that magnetic field also changes with the time, it can generate electric field. So due to this scenario, we can actually go in a loop. We can cause change in electric field to create a magnetic field, and also create that magnetic field which changes with the time. So because of the change in magnetic field, the a varying electric field is also generated. So I will write, without writing change, I will write varying. A varying electric field generates magnetic field, and also it can generate a varying magnetic field. If there's a varying magnetic field, it will create a varying electric field. So this continues, and this enables us to continue the propagation of wave across the space. The wave goes without stopping. Continuously goes without stopping because of this phenomena of varying electric field generating a varying magnetic field, and varying magnetic field again causing a varying electric field to generate. So in the space, it happens naturally. And because of that, we are able to receive electromagnetic waves from the sun towards the earth without any medium at all, and without any intermediate free electric charges or any kind of source supporting the wave to move forward. So this phenomena was very important, mainly because electromagnetic waves are important for us in many ways. So we can use this for data communications. And also, if you are doing power systems, you can transmit power, right? You can send signals with high frequency from one location to another location, where the signals will be able to carry energy. So if you are like working in a transmission section, when you are distributing, I think you are using high frequencies at the generation point, right? To generate and distribute the power to the subgrids or something, right? After that only you reduce the frequency and give to homes, like households, right? Yeah, sometimes because of the challenging environments in the medium. Mm. Yeah. Yes. Yes. Yeah. But yes, that is there. But due to that, we have now come up with technologies how to keep the energy level kind of above the threshold, such that we can send the signal for a large distance, right? One thing is we can increase the frequency. Once we have the frequency level high, and if we are sending it in an enclosed carrying carrier like a cable, and reduce the effects from the environment, the wave will have a kind of considerable strength or energy until a considerable length. After that, we need to actually repeat it. Again, we need to generate, supply some voltage and give some energy to that. Yeah, so that is possible. I mean, depending on the application that we are using. So if we are using it in a power system, for example, we are able to give sufficient energy at the distribution plants for the signal to be transmitted with some high frequency. However, like sometimes even high frequency signal to uh, do some like some amplification. Um, So low frequency signals, they can transmit for a high distance, uh, but sometimes we need to consider other factors as well. So like we need to get quick data, for example, in telecommunication or something. We can't wait for a very long time. We need high frequent data rates. For that, we need high frequency of transmission. So we cannot avoid such kind of applications. In that case, we can amplify in between. So as you said, the medium, depending on the medium, it will attenuate at some point intermediate uh, from the location. So we will be talking about Maxwell's law. So I will, uh, yes, right. Okay, so right, so Maxwell's law. So we will start with law one, right? So the law one is based on the Gaussian law uh, on electric field. So this you already learned. Uh, so this says that the total electric field displacement through a surface is equal to the volume, uh, the the charges enclosed in a volume, right? So I will write that law. You actually do not need to memorize these laws. I think actually I haven't decided what I will give you for the exam because I was a little bit busy. But mostly I won't be asking you to memorize the equations. I will ask you what it means. I will give you some equation, what it means. I will ask most. Sorry? Sometimes, like I will give the initial equations and then you might have to solve it and show some kind of a behavior or some kind of you need to show some kind of logic. Like, for example, in today's class, I will derive the fact that, like using Maxwell's law, we can generate I mean, we can show that we can generate an electromagnetic wave using varying electric and magnetic fields. So mathematically, we can show that the electric field and magnetic field combination forms a wave. So that fact you need to be able to mathematically show using the initial equations that I provide. I will ask you to use some initial equations. From there, you can start and you can derive it. So I will do the derivation in the class. You can likewise you might need to do something like that. Right? Yeah, 1 credit. So it's good, right? Not much. Uh, so yeah. Yes. So I think I'm also in a trouble because I don't know what to give. So so 1 hour is not enough for you to do something big. So maybe one question for the entire hour. You can solve that and you can try to find the answer. So I have, I think, how many classes do I have remaining? Like 3 classes, right? Until the, and I mean, including this, so apart from this, including this, only 2 more classes I have. Okay, so um, second week of July, I mean, when is your study leave starting? Do you know that? July, I thought your study leave starting on 17th. Yeah. Until 12th, I have time, right? If in case I do not have time to cover that, I might, is it okay if I do a video and submit into the LMS before the study leave starts? Then you can refer that, and I'm in the lab in my office all the time. You can come and ask if you have any questions. Apart from that, I will provide a sample exam paper for you to have a look. And this is the way that it might come, but I will not give the exam question there. Okay, so something similar I will give, and then you can prepare accordingly for the exam, right? Basically, the first Maxwell's law is basically Gaussian law for electric field. So so we have already gone through this. I will just write it down, but I think you already know this, and there's no right. So the total electric field that is displacing through a certain closed volume is equal to the total charge that is enclosed in that volume. So the differential form is given using this equation. So the divergence of electric field is equal to the charge within a certain unit volume over epsilon naught. So law 2 is based on the Gaussian law again. Gauss's magnetic field law. So right, this is magnetic. So total magnetic flux that is coming through a certain closed surface equal to 0. So a divergence of B equals 0. Third law is based on Faraday's law and Lenz's law. Faraday's and Lenz's law. Without charges. But charges are everywhere. Sorry, Maxwell. Mm-hmm. But in vacuum, we don't have charges in the vacuum. In that case, we do not have any other method, right? So, I mean, we that is where these equations come in, useful, right? In places where we don't have anything apart from the electric field and magnetic fields. Hmm. It is dying with the distance from the source. Now there's a source anyway generating the electric field. Yeah, but with the now with the time, the strength of the magnetic field and the electric fields that are generated distinguishes, attenuates. So with the time, it attenuates actually, naturally. And in the vacuum, of course, it goes constantly because of the, as you said, no medium. But once it reaches our atmosphere and the earth, it, yes, and it attenuates and dies after some distance. Okay. So the third law is based on Faraday's and Lenz's law. So we know that basically the Faraday's law and Lenz's law directly is considered here. So Maxwell's law, I mean, Maxwell, what he's telling is that we need all this combination of all these laws to explain the generation of an electromagnetic wave. We need these four laws to explain the behavior of electromagnetic wave and to prove that such kind of a wave will generate because of electric and magnetic fields. So he says that you can't just use one equation and explain the entire electromagnetic wave phenomena. He says that we need to have the effect of both uh, the both the both the electric and magnetic fields. So in the law 4 we have Ampere's law, right? So Ampere's law, I think we already learned about that in the last class. So it is talking about the generation of the magnetomotive force, which is equal to the total current that is applied through the surface bound by that path. The magnetomotive force around a closed path is equal to the total current, that is just total current through the surface bound by that path. So we can write it mathematically using this equation. Okay, so these are basically the four Maxwell's laws, right? Based on, four Maxwell's laws. So as I said before, Maxwell is showing us that after we generate a certain electric field that is varying with the time, then we can generate a varying magnetic field uh, based on the changing electric field, and the magnetic field will generate another set of electric fields. So we will try to draw it. I will try to draw it. Right. So uh, in order for us to generate an electric field, we need some sort of a source. So anyway, we need some voltage source, something that can generate us uh, a current, actually, right? A varying electric field uh, first can be, generated using a varying current, right? So if I take, for example, like we have antenna systems where we generate electromagnetic waves, then we first need to send through the metal wire, which is the antenna, varying current through by supplying some varying like voltage. So we need to provide some voltage, and then we need to vary the current across the antenna, and through that phenomena, we can start generating a magnetic field around this loop, right? A magnetic field is generated around this loop once we generate a varying current in the metal wire. So a varying current will generate a magnetic field, right? So once the current is varying, the magnetic field generated will also vary with the time. The magnetic field strength will also vary with the time, right? Then now what does this magnetic field do? Now that is the question, right? So the magnetic field, once we analyze each and every part of this loop around which the magnetic field is traveling, we can consider each and every part, and then we can analyze using the equations that we know, right? So we have learned the Ampere's law. So using Ampere's law, we can actually say that a curl of magnetic field creates a varying electric field. Okay, so I will draw it in here separately. So first of all, varying current generates a magnetic field, and due to the variation in the current, due to the varying current, uh, the magnetic field is also varying. Yeah, yeah, we are sending current up and down. Yeah. Due to varying current, magnetic field is also varying. Okay. So I will draw that in here. So I will use the same scenario, right? So we are varying current in here, and then we are generating a varying magnetic field. So once we are taking this magnetic field and the loop where we have the magnetic field, this loop we can define using the Ampere's law, right? Ampere's law said that we can generate a magnetomotive force around the surface around the edge of the surface across which the electric field is applied, right? So we have this equation for the Ampere's law. Right? Sorry. Yes. So we are considering unit points. So unit area at one unit area, the curl of magnetic field, the curl of magnetic field that is generated is equal to the amount of charge density and the amount of rate of change of electric field that is occurring, right? So because of the generation of magnetic field in this point, let's consider this specific point. So because of this point, now there's a varying magnetic field in that point, right? So because of this varying point, magnetic field, a varying electric field is generated based on this equation, right? So if this is present, if there's a curl of magnetic field present somewhere, it should be also, I mean, creating a varying electric field, right? So I hope it is okay with you, right? So this creates a varying electric field around this point, right? And the direction of that we can actually find using our right hand law, right? Uh, so I mean, for the equation to be existing, if there's a like now this first the current is generating a magnetic field, and now the magnetic field is independent. Magnetic field does not generate a current. Again, it is an independent thing that was a result of the current that was initially there, right? And then magnetic field now is doing something. It is generating a varying electric field according to this equation, right? So this is available, and therefore this also must be available around that area, around the specific area that we are considering. Yeah, varying electric field, varying potential. So around this magnetic field, a varying potential or a varying electric field is generated. So likewise, it will generate for each of these points around this loop, right? We will only consider this specific point for the moment. We are only considering that specific point just for our ease of understanding. Then after that, this electric field that is generated will also vary because the magnetic field is varying initially. So electric field will also vary. And then now electric field is behaving according to the like Faraday's law, right? So I mean, we can write another equation after this to remind ourselves the Faraday's law. So Faraday's law says like if there's a curl of electric field somewhere in the space, it is due to some difference in the magnetic field changing with the time, right? So in other words, if there is a electric field which is available at one point, it also causes this this magnetic field, some magnetic field which is varying with time to occur. So I hope it is clear to you. So the electric field, the presence of electric field generates a varying magnetic field. So once we take a certain point in the electric field loop, that we can draw a magnetic field loop which is generating because of the electric field. So if the electric field is going down, then we say that we have the electric field generating in the other direction. So I mean, using right hand rule, we can denote the direction of the electric field that is generating. Sorry, magnetic field. This is magnetic field. This is the current loop. Sorry, this is magnetic. This is the current loop, current carrying conductor. This is the magnetic loop, and this is the electric field. So, so likewise, I mean, this phenomena keeps on happening, and once we analyze each of these points, we can keep on we can keep on drawing electric fields or magnetic fields generating because of a magnetic field or electric field which was generated before that. Yeah, it is diminishing with the time. If it is a vacuum, it is remaining constant. Otherwise, with the time or with the distance from the source, the magnitude of the magnetic field and electric field diminish. Direction of the electric field and magnetic field must be checked by the right hand rule all the time. So I cannot say exactly it is in this direction or always opposite to a certain direction, but based on the direction of the electric field or magnetic field depends on the whatever the field which caused it. So electric field, if it is going down, yes. So right. So this will propagate over the space, and a series of magnetic field loops and electric field loops will be generated. So because of this phenomena, the wave will propagate over the space. So as you said, the magnitude of the fields will diminish over the time, and sometimes we will have lesser strength in the electric and magnetic fields. So anyway, the wave will propagate in this direction and will diminish at a certain time. So that is how we generate electromagnetic waves based on the different mathematical laws, and based on I mean we analyze it using mathematical laws, but basically this is how electromagnetic waves are getting generated in the space. So I hope you understood something. So you can study about this later as well once you are free, and then you can try to understand how it's occurring. So basically, those are the things that I wanted to cover today. So I have some more uh, content to cover. So I will try to cover it. If I'm not able to cover it during the classes, I will do a certain video and try to upload to LMS and try to cover that section. To actually, for me, it's difficult to do this 1 hour lectures for 1 week and cover this kind of mathematical stuff, which is time consuming, and it takes some time for you to also understand those concepts. Therefore, since the time is not limited, I will try to cover it with some additional materials. If you have questions, you can let me know. Yeah. Yeah. Entire. Yeah. Yeah. But the average we can take for a certain direction. Like for a certain direction, we can take the average of all the variations along the loop, and we can I mean if a certain wave is going in a certain direction, we can take the average of the electric field or magnetic field along that direction, and yeah, yes, yes, yeah. So yeah, at each point that will be generated. However, based on the direction that we select for the wave to propagate, we design our electric field strength to vary in a certain way, such that the wave is only going in that direction. So for that, we are actually designing our antennas and our like equipments such that the electric field and magnetic field only varies in a certain direction. Based on that, the wave will propagate in a perpendicular direction to both the electric field and magnetic field. So we will talk about that also in the next classes, right? So, do you have any questions? Yeah. Yes. Actually, 50 hertz actually might do, but not in a large scale. Actually, I mean, as you know, like electromagnetic waves are propagating in like 3 × 10⁸ kind of like velocity and the high frequencies. We consider electromagnetic wave spectrum for waves which are above a certain frequency, like kilohertz, megahertz, gigahertz, that range. So for 50 hertz, there is not much effect of it creating magnetic field effect actually. Yeah. Yeah. I mean, now the source. No, the voltage supply is given. I mean, there's a top conductor and bottom conductor, and it's a transmission line which is connected to. I mean, it is like a coaxial cable which is connected to the antenna. So antenna, if it is a metal wire, we can connect the ground plane of the coaxial cable to the outer conductor of the antenna, and to a inner surface. So inner conductor of the antenna, we can connect the top conductor or the main, I mean, live conductor of the coaxial cable to the antenna. So antenna is like this. So outer surface will be connected to the ground plane. There could be some internal conductor, then it is connected to the live or the top conductor. Yeah, single wire antenna. So there's anyway a ground plane is there. I mean, like, yes, there has to be a return path. So single wire means like you're meaning in phones and so on. Yeah, so that is, yeah. So now so that microstrip, now it is a microstrip antennas. So this antenna will be on the top conductor of the PCB. PCB has a ground line. So the antenna will be on the top conductor, and the ground plane will carry the, I mean, will be the return path of the currents if it is. No, actually, we can add a capacitor also to do matching of, I mean, matching to match the impedances, or else actually there's no necessity that we need to add a capacitor, but it is designed in such a way that the current is. Yeah. Yeah. The metal wire, you mean? It's just that we are changing current through the metal wire on metal conduct only. It doesn't need to connect to anything. Yeah, just the power supply is connected to this. Uh, yeah, maybe you can learn it if you want separately by referring something regarding those systems. No problem. So thank you so much for attending to this class.